Logic gates, syncing and sourcing. In this presentation, we're going to be looking at the differences of a syncing logic gate connection versus a sourcing logic gate connection and how that affects the operation of the load. Now, it should be understood that loads or components can be connected to logic gate outputs in one of two different ways, syncing or sourcing. Depending on the connection used, the operation will change. Well, let's take a look. In a sourcing system, this is the one that we are most used to. This is a NOR gate. We've got a negation on the output side of the OR gate. The load is connected to ground and to the output. That means load current is sourced from the logic gate to the load. Well, let's see this in operation. Right now, my output should be high. That's because I don't have any inputs that are high and I've got a negation. So that means that with 5 volts applied to one side of the LED, the other side should then have a connection to ground and the LED should be on. If I were to press one of the push buttons, let's say the lowest one, I would cause a high signal and that would then result in a low coming out from the output and the LED turning off. If we contrast this operation to a syncing component, it's a lot different. The load is now connected here to the output of the logic gate, but also to the positive side of the source supplying the system. Load current flows from the positive side of the source through the load and syncs to ground through the logic gate. So let's see how this one functions in a system. Right now, I have a high signal on the output side of my NOR gate. And what that means is that high is here, but look what happens now. I've got a high on the bottom and a high on the top of that LED. Now it means that the potential difference across that load is actually 0 because I have 5 volts here and 5 volts here. Now, when I press down that lower, the last push button, the LED should change state. So the LED is off right now. When I press down that push button, I have a high signal coming into my NOR gate. Low is then present below the LED, which means there is a potential difference across the LED. The LED comes on, and it then flows through the NOR gate back to the source. Well, let's take a look at some practical examples, starting with an alarm system. A basic alarm system for doors or windows, and in this system, when the window is open, we've got a high signal, and when the window is closed, I have a low signal. And this will be a classic syncing connection for my output. So I've got a magnetic reed switch here on my window, and when someone comes along and they try to open the window, what it does is it moves the magnet and the contact closes, and that will give me a high signal. Now a high signal is coming into my OR gate, and that then causes an output of +5 or high to go to the alarm circuit, hence alarm sounds. In the transportation industry, there's lots of digital logic controllers that are utilized, and here's an excellent example. For this one, the landing gear in an aircraft are going to have sensors. When they're extended, there will be a low signal, and when they're retracted, there will be a high signal. And these two logic gates are then going to come through to two separate LEDs. The red LED will come on when the gear is retracted. This is a syncing connection. Over here, the green LED, all gears extended. So this is a sourcing connection. So red light, green light, two different types of logic gates. And this is the landing gear that we're kind of referring to on the aircraft. Now, before we get going, it's important to realize that you can demorganize these. These are really demorganized equivalents, which means if you're having trouble following through this operation with me, you could simply change this one to be the same as the top logic gate symbol, or you could change the top one to be the same as the lower logic gate symbol. Just a handy hint. Well, let's take a look at what happens right now. All of my gear is extended, which means we have a low signal coming from each one of my landing gears going back to these logic gates. What that means is that for the top one, I have a output of 1 or a high of 5 volts, and it's connected to the 5-volt source. That means that right now, this LED is off. If we look at the one below, I should have a high signal coming out, and due to the connection of this LED, we see that the light would be on. All landing gears extended. Now in this situation, all of them are going to be retracted. So we have high signals going back to all of the inputs and all of my logic gates. On the top one, the red LED we can see here, there is now a potential difference across the LED, and it is going to then flow through the logic gate to ground. So this one would be on. The lower green LED has a low signal coming out of the logic gate, which means that this LED will be off. So an interesting application. Let's see a problem. A problem with the landing gear while landing. Two of them are retracted, but the nose landing gear is not. It is low. Or low means extended, my apologies, and retracted means high. So this one is out and those two are still in the fuselage. So that would result in two highs and a low and two highs. Well, what would be the ramifications on our LEDs? Well, in this case, we're going to see that we have a low coming out of the output of this logic gate, and that means potential difference. Red LED will be on. That means it's saying gear is retracted. That means some of the landing gear is not extended, waiting for impact on the tarmac. This one will remain off, and that is one that just says all gear extended. So that kind of makes sense. This green light will only come on if all three of the landing gear are extended simultaneously. Here are some more examples of syncing and sourcing logic gates. So on this one, we have a couple of tanks and a couple of proximity sensors. The green light is on if both tanks are greater than a quarter full. The fluid in front of the sensor will give a high signal. The green light indicates both tanks are greater than a quarter full. And we can see the connection here. So right now, we've got capacitive proximity sensors that are being used to determine the level of liquid inside the tanks. So right now, we don't have any liquid in front of or covering those capacitive sensors, and that means that both of them are sending a signal of low or 0. That means that the output of this logic gate is 1 or high, and that means there is no potential difference across the green LED. This means the LED remains off. If we then increase the fluid level in one of these tanks, I would then have a high signal coming back to input A, and the result would be that the output for this logic gate would go to high, and there would be no potential difference across the LED, which means the light would be off. If both of these sensors then have liquid in front of them, they are sending both back a signal of 1 or 5 volts high, which means that the output will be low. And when the output is low, it means that the LED will be on, and that's because there is a potential difference across it. Let's take a look at a second industrial process. Red light is on when one or both tanks are less than a quarter full. Again, fluid at the sensor of this capacitive sensor is going to be a high signal sent back. And we can see the connection here where the output goes to the load and then to ground. In this situation, we should have a high signal going back to this logic gate, and because of the inversions on both the inputs, this negative OR gate will have a low signal coming out, which means, well, it's off. The LED should not be lit. If, however, one of these tanks falls below and our capacitive sensor no longer has fluid in front of it, input B would drop to 0 volts or low. And the result of that would be that we have a high signal coming out from the output, and the LED would be on. If both of these fell below quarter full, then both of them would be sending a 0 or low signal back to this negative OR gate, in which case we would have a 1 or high output and the red LED would be on. So I hope this was helpful in understanding how the difference in sourcing versus syncing of a logic gate and its output can change its operation.